What's the farthest you've ever been from your home? Have you ever left your city, your state, or even your country? And what if I told you it's possible to leave our planet? Unless you're one of the few people who have already left Earth, probably not. But we all have a place we know best, our home. The farther we go, the more different things we find, and new experiences emerge, full of opportunities to learn. And when we return, we're changed, even if just a little bit. This also applies to humanity. Our home is the blue planet of the solar system. But leaving home has helped us understand more about Earth and ourselves. Traveling to the moon advanced aerospace technology and reflected the tensions of the Cold War. Exploring Mars with probes has given us insights into Earth's history. Sending a golden record with information about humanity on the Voyager forced us to reflect on who we are. Exploring the universe and its mysteries is not just a technological and scientific exercise, but a unique opportunity to reflect on what it means to be human. So, how far can humanity go? How much of the universe can we access and understand? And what will we learn from it? But before we understand the cosmic boundaries, we need to understand a bit about light. And that's where the concept of light cones comes in. No spacecraft or vehicle with mass can travel faster than light. This is one of Albert Einstein's relativity postulates. Light is the fastest thing in the universe. No matter where you want to go, light gets there first. And this has an interesting consequence. If light can't reach a place in a certain time, neither can you. The closest star to the Sun is in the Alpha Centauri system, more than 4 light-years away. Sunlight takes just over 4 years to make this journey. So, a spacecraft leaving Earth couldn't get there in 2 years, nor in 3. A spacecraft would take at least just over 4 years to reach the nearest star. In other words, Alpha Centauri is out of reach for us in the near future. The problem is that the universe won't stand still while we explore it. It's expanding at an accelerating rate, growing in size faster and faster. Distant galaxies are moving away from us, and not only that, they are moving away faster and faster. In 150 million years, more than 99% of galaxies will be too far away to be visited. To talk about cosmic distances meaningfully, we need to account for the universe's expansion rate. Physicists solve this using something called comoving distances. The true distances in the universe, called proper distances, change with the universe's expansion. Comoving distances account for this expansion, so they are relatively constant. Comoving distances between galaxies only change because of the galaxy's actual movement, not because of the universe's expansion. Basically, comoving distances freeze the distance measurements for the universe today. The downside is that this freezing of distances distorts velocity measurements. In comoving coordinates, it seems like light slows down in the future and speeds up in the past. This changes the shape of our future light cone, which ceases to be a cone and becomes more of a parabola. With comoving distances, we can talk about the true limits of the universe. And the first limit is the horizon of the observable universe, or the cosmic horizon. It is defined by the past light cone, that is, all the places in the universe that had time to send light rays to Earth. In comoving coordinates, the past light cone goes back 13.8 billion years, which is the time since the Big Bang, and forms a bubble 46.4 billion light-years around our planet. All the light that reaches any telescope on Earth is part of the observable universe. And here's a note. If the universe is only 13.8 billion years old, how did light travel 46.4 billion light-years in that time? This is a consequence of the universe's expansion. The effective speed of light is affected by the expansion of space itself. It seems that light was faster in the past. That's why it's important to use comoving distances, because without them, we would have to actively compensate for the expansion effects. And that wouldn't be easy at all. The distance of 46.4 billion light-years is called the cosmological horizon. To be precise, No light ray can reach us from these extreme locations. The universe was opaque in the past, and light signals couldn't travel. The most distant light ever observed came from the galaxy JADES GS Z13O, 33 billion light-years away. The past light cone determines the observable universe, and the future light cone determines the universe that can be affected by our actions, that can be reached even if by weak radio waves traveling billions of light-years. A radio signal emitted today from Earth will eventually reach all the galaxies in the universe within a radius of 16.5 billion light-years from Earth. This is the reachable universe. And with spacecraft near the speed of light, a human could theoretically reach almost all galaxies in the reachable universe. To reach the limits of the reachable universe, one would need to move almost at the speed of light, which is currently impossible. It makes more sense to invest in fast spacecraft before trying to reach stars and other galaxies. If in 100 million years human spaceships become just 2% faster, it's still worth waiting. We'd avoid an uncomfortable scenario where an initial interstellar mission is sent on a centuries-long journey, only to discover that a much faster ship was invented during the trip and got there first. So, how to colonize as much as possible of the reachable universe? A spacefaring civilization would need ships capable of three things: moving through interstellar distances, transforming matter into energy, and creating more ships capable of these two things. Such a ship is called a von Neumann probe. How close are we to making such a machine today? Well, let's break it down. Today, we use chemical propulsion ships to move through space. They are fast by human standards, with speeds of tens of kilometers per second. But that's still too slow for interstellar travel. There are 10 trillion kilometers in a light year, and 4 light years to the nearest star. Chemical rockets are not only slow, but they also burn fuel too quickly to accelerate for long periods. There are two strategies for interstellar travel that seem to work in theory: powerful ships with extreme acceleration and ships that accelerate gradually, but can accelerate for long periods. An example of the first strategy would be a nuclear rocket like Project Orion. Such a rocket would use nuclear explosions as propulsion. Very cool, but extremely dangerous. We need to learn to cure all forms of cancer before putting a human on such a rocket. The slow acceleration strategy has already been used in satellites and probes like ion propulsion. Ions are electrically charged atoms, and charged particles can be efficiently accelerated with electric fields. An ion-powered interstellar spacecraft would be powered by a nuclear engine similar to that of a nuclear submarine, without needing to explode anything. The energy would last a long time, ideal for accelerating halfway and braking in the final half. Whether with a ship using nuclear explosions or long-term propulsion, such a ship should reach 20% of the speed of light, enough to travel to Alpha Centauri in 40 years. A few decades is not fast on a human scale, but it is almost instantaneous on a cosmic scale. When it reaches the other star, the ship should be able to refuel. Ideally, it would master nuclear fusion. Nuclear fission energy is already mastered, but it is less efficient than fusion, which uses hydrogen and helium as fuel, the most abundant elements in the universe. With the fuel issue solved with nuclear fusion, the ability for the ship to replicate remains. There are many stars in our galaxy, hundreds of billions, and trillions of stars in other galaxies. You can't directly manufacture that many ships. The most efficient strategy is to use self-replicating ships. In practice, humans can start space colonization, but robots will finish the job. Robots with artificial intelligence good enough to make decisions on their own during the mission. Even if only half of the ships succeed, that's still enough. A self-replicating ship moving at 20% of the speed of light and capable of making other ships would occupy the galaxy in a few million years, in a conservative scenario. Intergalactic travel is not much more technologically challenging. It's just a change of scale. Maybe a replicating ship would stop at the edge of a galaxy to create a larger version of itself, a super intergalactic ship. Or it would build a funnel to collect hydrogen in intergalactic space. The maximally observable universe combines the reachable universe with the observable one. It's what we could see if we colonized the entire observable universe with von Neumann probes carrying space telescopes. We would turn 16.4 billion light-years around us into a giant telescope. With it, we would see any galaxy today up to 79.4 billion light-years away. This is the combination of all observable universes from all the stars in the reachable universe. It's the final horizon of the universe. There is a large part of the universe that, in theory, can be seen but that we will never see. The frustration is negative but points to something positive. Human curiosity refuses to know limits. What's your opinion on this? Do you think humans will ever leave the solar system? Type your thoughts in the comments. Thank you very much and see you next time.